Hello. Today we have the opportunity to discuss about one of the laws of electromagnetism, and this laws of electromagnetism that we are discussing today is the so-called Ohm's Law. And Ohm's Law, maybe you are already familiar with this law, is simply relating the voltage and the current that we can have in a conductor material, right? And we know that this voltage and the current are related to each other simply through the relation that the voltage is equal to the current, which is I, multiplied by some constant R, right? And so R is the so-called resistance of the material that is that is carrying this current, right? Usually the carriers of these currents are metallic, right? Are conducting materials such as metals. Metals are very good conducting materials, right? Now, so this is Ohm's law, and this is probably, well, you probably have seen this many times already. Another question is, where does this come from, right? Because, well, we as physicists, we like to know about where things come from, are not taking things from granted, right? And so today I'm explaining some, well, in very few steps, how we can derive this rule that applies to metallic materials, right? And so let's start with assuming that we have a piece of material, right? So we have our material here. So this, we assume that has some length L, right? And let's also assume that this cross section that we have here has an area A, right? So far, so good. And then imagine that, so this is some metallic, a metallic material, and now let's assume that we have some current that is going through this material, right? So let's have a current I that is flowing through this material, right? So what happens? What's happening inside, right? Well, this material, of course, is made of atoms, and in these atoms there are electrons. And whenever we have electrons that can move around and we expose them to some current, well, they start to move, right? So if we have electrons that can move in space freely, right, and we apply some current, right, we apply some electrical current, or we have some current, it means that these electrons are moving to the opposite direction of the current, right? And this is simply because of a convention, right? If the current is going to the right, the electrons are going to the left, right? But this is a convention. There is no particular reason why it's been like that, but that's the convention that people usually assume. Now, if we have this current on this material, it means that well, there is something that is making these electrons move from one place to the other, right? Things don't move on its own. They only move because something is making them move, right? And this something is a force, of course. So if the electrons are moving to the left, in this case, it means there is a force. It means there is a force that is pushing them to the left, right? There is a force that is pushing the electrons to the left, right? Now, which force of nature is able to move electrons, right? So we can say about, okay, gravitational force can move electrons. Okay, yeah, that's true. But the effect of gravitation on electrons is very small. There is another force that is much more stronger than gravitation, and that's the electromagnetic force, right? So the electromagnetic force, so it's a force that is proportional to the charge, and this charge is moved by the presence of an electric field. So the electric field it's a field that permeates the entire space. And so if we have a field that goes from here to there, and we have some electron in the position, so if the field is going from here to there, the electron will move in the opposite direction, right? And so to make things consistent with this, so I said that if the field goes in this direction, the electron goes in the opposite direction, and that's because electrons have a negative charge, right? That's minus E times the vector of the electric field, right? So having a force that is moving the electrons to the left is implying that we have an electric field that's pointing to the right. So in our sketch, having electrons moving to the left means that we have an electric field that is moving or that is pointing to the right. So coming back to our sketch in the metal, it means that there is an electric field that is going in this direction, right? And now, well, let's assume that we have that this material is uniform, that there are no impurities in the system. So more or less every bit of the material is equal to the bit on the side. And so that means that the electric field, well, we can write it as, or we can say that the electric field being constant on this stretch of material is inducing a difference of potential between two bits of the material, right? So we can say that we have some potential here V plus and some other potential here V minus, and so we have V plus minus V minus. That would be well, different from zero, right? So we have a difference of potential, of electric potential, right? And that's induced from the presence of the electric field, right? And so, of course, we can say that this difference of potential, this B plus minus B minus, is actually the magnitude of the electric field multiplied by the separation between these 2 points, right? So that's coming from the potential part of the electric field. Now, when we have this current, and if we look at, so we have our bit of conductor, our bit of chunk of conductor. So if we look at some section here in between, we look at a cross section here, we will be seeing not the entire current, but we will see some density of current, right? So this density of current we call J, so that would be the density of current. So that's how much current we have per unit area on this material. So that would be the total current divided by the area of this material. So remember, this here is what we call the area, is A, and I is the current that is flowing from one place to the other, right? And now, whenever we have this current, it's because we have some electrons. As I said, we have some electrons that are moving from one place to the other, right? Now, these electrons, well, in this material, we have the electrons that are occupying the matter with some density, right? So if we say that we have a density of electrons n, because why not? We can have an arbitrary density of electrons. So this n, that would be the number of electrons per unit volume, right? So this current would be the density of electrons per unit volume multiplied by, of course, the charge of the electrons. That would be minus E, right? And so a current is charges in movement, right? And so we have to multiply these charges by some velocity, right? And this velocity is the velocity at which these electrons are going from one place to the other, right, on this conductor. Now, but again, what is making these electrons move? Right? These electrons are moved because of the presence of an electric field. And so it means that this velocity with which the electrons are moving is proportional to the electric field, right? So there is a proportion, a constant of proportionality that we call lambda here, that is making the relation between the magnitude of the electric field and of the velocity with which the electrons are moving from one place to the other, right? And so what that means is that we have made a relation between this density of current, which is minus E minus NE times lambda, this constant of proportionality between the velocity and the electric field, multiplied by the electric field, right? And now we have a relation between the density of current, right? Remember, this density of current is what we have here, right, in this cross section of the material, and the electric field that is going from one place, so from 2 points in the bit of metal, right? And of course, we can put all of these constants. So the density doesn't change in the material, the charge of the electron doesn't change either. The constant of proportionality between the velocity and the electric field also don't change. And so we can call this with another Greek letter, the sigma, and we can write that the density of current is equal to sigma multiplied by the electric field, right? This sigma that we have here is the so-called electric conductivity. The material, and of course this depends on the actual material that we have. So for a very good conductor, this is a very large number, and for a very good resistor or insulator, this is a very small number. Right, but the point is that we have found this very nice relation between the current and the electric field, right? So we have found before that this density of current was given by the current divided by the area, right? And we also know that the electric field can be expressed in terms of the potential that we call V instead of delta V, because, well, potentials are always a difference of potential, divided by the length of the material, right? And now this is getting very close to what we're going to find, because if we say that the current is equal to the area times the conductivity divided by the length, this is still multiplied by the potential. Well, this looks very much like the Ohm's law that we found at the beginning, right? Where we have that the potential was equal to the current times the resistivity, right? So we can rewrite this. So the potential is equal to L divided by A sigma times the current, right? And so to have these two things equal, we need to call this the resistance, right? And so for conducting materials, this equality is true. So the resistance of the material is given by the geometrical aspects of the conductor, so the length and the cross section through which the electrons are moving, and the electric conductivity of the material, right? And so this is the demonstration of where the Ohm's law comes from, right? Now, although this Ohm's law applies to a very large range of materials, so particularly conductors, not all the elements of circuitry obey this law, right? And so what you can look at as a bit of a homework to see which element of a circuit does not obey Ohm's law, right? So that means that if we increase the potential, or if we increase the potential across a circuit, the current will not increase linearly with the potential, but will have a different behavior, maybe an exponential or something similar.